We're doing integral vector calculus, and we were talking about the work integral, and we're going to get to a method called Green's theorem. But to do Green's theorem, you need to do double integrals. So let's review double integrals. You should know it from calculus, but let's go over it again. You got a function of two variables, x and y. So the function itself would then form this surface up here. Surface is c equals the function of x and y. For a little chunk in the area down in the xy plane, so this little chunk here, that has an area. And if I look at the parallelogram or parallelepiped, I guess it is, up to the surface, that would be a volume of this parallelepiped. And if I summed over all these little areas in the xy plane, I would get the volume under the surface. So that's what we do. We take the limit, this area goes to a differential area, and the sum becomes an integral. And if you think about it, you could take a slice. So have a slice of that volume would be a thin sheet. You'd have an area times a little delta in the other direction. That'd be a little thin volume of a thin sheet, and sum over all the thin sheets. That would be iterating the double integral by first doing a single integral over one variable and then outer integral over the other variable. You can do that if the shapes in the xy plane are amenable to that, and if they're not, you'd have to split it up somehow. But in anything we're going to deal with, you can deal with the double integral by iterating integrals. If you integrate over y first, the limits of the inner integral could be functions of x. By the time you get to the outer integral, the limits need to be constant. The big thing you need to think about is the region of integration. You look at this. Interpret every limit of the integral as a function. This integral is over y. Y comes first. So this lower limit means the function y equals minus x squared. So draw it. That's a parabola down. Upper limit is y equals x squared plus 1. That's a parabola that goes through the point 0, 1 upward or opens upward. The other ones are x equals minus 1, draw that line. X equals 2, draw that line. So the area you're integrating over is this little shaded region here. And it really helps to draw it. In fact, I really have to draw it myself every time I do a double integral. Try to just think through it, you're probably going to have trouble. And you need to worry about what order of integration, over x first or over y first. Like say this one, if you integrate over x first, pick any y. Integrating over x first means you first go that way, horizontally, along the x-axis, parallel to the x-axis. For some of these, see if this were the y you picked, some places there are not in the region of integration. You just started your x here and went to the right. You're going to encounter places where it's not in the region of integration. In this case, if you integrate it over y first, each x in this interval, you can just go from one boundary to the other without interruptions. So just based on the region of integration, you'd like to integrate this guy over y first. Let's look at this guy. Here the boundaries are x equals y squared. What is that? It's a parabola opening to the right. X equals 0, which is this line here. Y equals 1, that line there, and y equals 2, that line there. The region these are the boundaries of the region. So that means this shaded region is the region of integration for this integral. If I integrate over x first, as y goes for any y between 0 or between 1 and 2, I stay in the region of integration. And it's all the same. I would just go from this boundary, x equals 0, up to this boundary, which is x equals y squared. If I integrate it over y first, boundaries change. From x equals 0 to 1, y would go from 1 to 2. Once x goes from 1 and up, the lower boundary is y equals the square root of x. So you'd probably, in this case, like to integrate over x first. Sometimes it depends on your integrand. But in this case, the integrand is easier to do if you do it over x first as well. So we'll do that. I'm not going to go through everything here. We integrate that very same variable over x first. X first. So x goes from 0 up to y squared. And then y just goes from 1. Once you've really got, especially if you drew the region of integration, writing these limits of these integrals is much easier. Getting the limits correct is a big deal. Don't just, well, I had everything correct with the limits. The limits are crucial. That's the biggest part of these problems. If you do that, I don't know, this is just kind of regular calculus. End up with these two guys. This integral, you'd either need to look it up in a table or you do this integration by parts business. So this was kind of a tedious integral to take. I'm not going to go through that. Once you set up your limits right, it turns into normal calculus, normal just taking the integral. Here's another case. You might be given this, but maybe it's more convenient if you do it integrated over dy first, do dy dx. You got to think, well, what are the limits? And in this case, if you look at that integrand, how would you integrate that over x? E to the something over x. Do e to the y first. Just the integrand makes it look easier. So let's look, what is the region of integration? Integrating over x first, function is x equals 2y or y equals a half x. That's a straight line up to x equals 2. X starts here along this line, goes right to 2. And y just goes from 0 to 1. That shaded region is the region of integration. So if I integrate over y first, I'm going to go from this lower line, which is just y equals 0, up to that line, which is y equals a half x. Here are the new limits. And there, I'm just going to take the integrals, and I'm not going to. When do you not have to iterate? You can just multiply the two guys. When your integrand is just a product of two functions that are just functions of the separated variables themselves. So f is just a p of x times q of y. And the other thing you need is all constants for the limits. You can't have, in this case, you can't have this guy being a function of y and this guy, or this guy being a function of y. And that is the case, you can just multiply, you can break it up into two integrals and multiply the two results separately. We like when you can do that. It makes things simple. I'll cover polar coordinates in a separate recording. And I know this is all basic review. You think you know it, but you're probably a little rusty.